The vast majority of weekend prospectors walk past the very rock that once made entire mining towns boom. Milky white quartz with rusted streaks or orange bruising often litters old tailings or washes, and yet most overlook it, assuming it's barren or already picked clean. But a key diagnostic mistake is treating quartz as decorative rather than diagnostic. In reality, some of the richest free-milling gold is still found inside seemingly bland quartz fragments, especially when they're tinged with oxidized iron or fractured at sharp, unnatural angles. The hidden value lies in how quartz hosts gold, not on its surface but deep within its microfractures, sealed during hydrothermal flows. These silica-saturated fluids under high temperature and pressure deposited quartz veins across shear zones, faults, and cracks. Gold, being among the last minerals to crystallize from those fluids, often precipitated out as metallic inclusions, trapped within the cooling quartz. If sulfides like pyrite or arsenopyrite were present, the gold may have ended up inside those metallic shells instead, shielded from view and hammer. That's the trap. Gold in quartz rarely shows as glitter. It's usually bound in or next to sulfides, and the host quartz looks deceptively dull. Yet a trained eye can spot clues. Iron-stained veins, especially those near historical diggings or intrusive rock contacts, suggest pyrite decay and possibly gold encapsulation. Fractures with hairline rusting or boxy patterns hint at oxidized sulfide remnants. The key difference isn't color alone but context. Isolated red streaks with no structure tend to be worthless. Branching veins with cubic shapes or layering could signal deeper potential. Even a simple hardness test, quartz approximately Mo7, can begin the distinction. If the rock crumbles unusually around red spots or feels brittle where it should feel glassy, sulfide breakdown may already be underway, a signal to examine further. In creek beds, weight in hand is a second clue. Heavier than expected quartz could contain iron minerals or even native gold. Such samples should be retained for controlled roasting, not dismissed. This overlooked category, rusty quartz with no visible gold, has misled generations of hobbyists into discarding pieces that a small-scale furnace could reveal as profitable. But what exactly separates a piece worth roasting from just another stained rock? That test begins with a closer read of the rust. What many mistake as surface staining is often the most diagnostic clue a rock can offer, if you know what type of rust you're looking at. Most red, orange, or brown hues in quartz come from iron oxides, but not all iron oxides are created equal. The difference between a worthless weathering stain and a gold-associated sulfide decay starts with both distribution and texture. A general haze of orange across a rock's surface tends to be superficial, the result of general oxidation from water and air. But sharp, angular staining, especially in cracks, veins, or around cubic shapes, suggests a more complex origin. That origin is often pyrite. When pyrite breaks down through oxidation, it leaves behind iron oxides like hematite or limonite. These are not only color cues, they're metabolic footprints. Hematite typically forms red to reddish-brown crusts, while limonite is more yellow to earthy brown and often blotchy. In quartz, limonite often pools in pits or honeycomb textures where sulfide minerals once resided. These textures matter. A smooth red smear is far less interesting than a jagged, pitted vein edge caked in yellow-brown crusts. The latter hints at pyrite decay, potentially from sulfides that once hosted native gold. Under a loupe or strong hand lens, you may also spot tiny black or metallic flecks embedded along fracture lines or within cavities. These could be remnants of magnetite, hematite, or even visible gold, but the crucial context is their pattern. Do they occur randomly, or do they trace linear or dendritic paths? Do they surround voids or appear as ghost outlines of former crystals? These questions guide whether the quartz's rust is passive or reactive, merely cosmetic or chemically significant. Field conditions affect oxidation depth, too. In arid zones, oxidation can be deep and complete, making it harder to spot fresh sulfide traces. But in moist or seasonal environments, oxidation may only affect outer layers, leaving the core of the quartz intact and preserving its gold-bearing potential. Breaking a rock open to check internal color is essential. A white or pale interior with red-streaked outer crust often suggests superficial staining. But if oxidation seeps several millimeters into the rock, or if interior pyrite cubes show partial decay, that's a roasting candidate. Finally, note any greenish tinges, especially near arsenopyrite zones. These may indicate secondary minerals like scorodite or jarosite, further proof of sulfide breakdown and by extension, possible gold association. These chromatic signals can guide your first field sort. helping prioritize which quartz chunks are worth the weight and fuel to roast. Gold doesn't just land in quartz by accident, it's trapped there by one of the most reliable chemical filtration systems in nature. Deep underground hydrothermal fluids, water superheated by magma and loaded with dissolved metals, rise under pressure through cracks in the Earth's crust. These fluids are rich in silica, the essential ingredient for quartz, and they often carry sulfur, iron, arsenic, and crucially, gold. As these fluids migrate toward cooler zones, the chemistry shifts rapidly. Pressure drops, temperatures fall, and the metals begin to precipitate out. Quartz crystallizes first, building the structural veins. As the silica cools and locks into place, the remaining metals in the solution have less space and lower solubility. Gold, often carried in solution as a chloride or sulfide complex, begins to fall out, either as free metal or as inclusions within other sulfides like pyrite or arsenopyrite. In this thermal cascade, quartz acts as both host and trap. The tighter the fracture zone, the more pressure change the fluid experiences, and the more likely it is that gold will drop out and become enclosed within the quartz matrix. This is why gold-bearing quartz tends to cluster around shear zones, fault intersections, and intrusive contacts, places where thermal gradients are high and fractures are plentiful. These physical features create open spaces and pressure differences that encourage both quartz deposition and metal precipitation. Not every quartz vein carries gold, but veins that formed under the right conditions, especially those with visible sulfides or multiple generations of veining, are much more likely to host it. It's also why gold often occurs with pyrite and arsenopyrite. These sulfides crystallize under similar temperature and pressure regimes. Gold can be mechanically trapped within their crystal structure or form as submicroscopic particles inside the sulfide grain. In such cases, the quartz you're looking at is essentially a mineral tomb. The gold is entombed in sulfides, themselves encased in silica. And without breaking those structures, the gold remains invisible to the eye and inaccessible to the pan. Understanding this sequence, silica deposition, sulfide crystallization, gold precipitation, is critical when selecting samples for roasting. If the quartz formed too early or in low metal zones, it may be pure and bright but barren. If it's riddled with sulfides and alteration halos, it may still contain recoverable values. And that's where roasting plays its role, not in creating gold, but in freeing it from its mineral cage. In gold prospecting, few minerals walk a finer line between false hope and real promise than pyrite. Known to most as fool's gold, pyrite Fe2 deceives by its metallic luster and brassy color. But in the right geologic context, it's a highly reliable vector for real gold. That's because gold and pyrite often form from the same hydrothermal fluids, under the same pressure-temperature conditions. Pyrite, being more chemically stable, often crystallizes first, providing a structural matrix where gold can later deposit as microscopic inclusions or nanoscale films. In these inclusions, the gold is not visible. It's locked inside the iron-sulfur lattice, completely shielded from mechanical recovery methods like panning or crushing. This is what's known in mining as refractory gold, gold that cannot be liberated through gravity separation alone. However, heating pyrite to 500–700 degrees C in the presence of oxygen breaks it down. The sulfur oxidizes into sulfur dioxide, a pungent, acrid gas, and the iron oxidizes into hematite or limonite. What remains, if you're lucky, is a dark red, crumbly residue with gold specks now released from their sulfide prison. This oxidative decomposition is the entire logic behind roasting. It strips away the iron-sulfur envelope that sealed the gold. But it only works if gold was truly present to begin with. Pyrite without embedded gold is just iron oxide waiting to happen. That's why visual cues, like pyrite in quartz veins near shear zones or altered wall rock, are only the first step. It's also why roasting small samples is key before committing to full-scale processing. There's a hierarchy to pyrite-based gold associations. In some cases, gold is finely disseminated throughout the pyrite grain, what geologists call invisible gold. In others, it exists as tiny particles on the edges or cracks of the sulfide crystal, making it slightly more recoverable. And in the best cases, gold forms late, sometimes filling spaces after the pyrite has fractured, leading to free-milling specks adjacent to sulfide remnants. Roasting targets these internal structures, breaking down pyrite's tight crystal lattice to leave the gold either exposed or embrittled for mechanical release. But not all yellowish metallics are pyrite. Chalcopyrite, arsenopyrite, and even some mica varieties can masquerade. Each behaves differently under heat. Arsenopyrite, for example, emits toxic arsenic oxides when roasted, an important safety and legal consideration. Still, the ability of pyrite to host gold makes it an essential field clue. Where you find clustered cubic pyrite, especially if it's decayed, rust-colored, or loosely bonded into quartz, you may be standing over a roasting-grade ore. It's a common beginner's instinct: see a chunk of rusty quartz, swing a hammer, and hope for a glittering surprise. The satisfying crack and glassy shards suggest progress, but this brute force approach often ends in disappointment. That's because even when gold is present, it's not typically visible on first fracture. Gold tied up in sulfides remains trapped inside microscopic mineral structures, often surviving both hammer blows and coarse crushing without being freed. Mechanical breakage simply doesn't reach the submicron scale where much of the valuable gold resides. When prospectors crush quartz manually, whether with a sledgehammer, jaw crusher, or mortar, they usually aim for visible gold or free gold that can be separated by gravity. But gold embedded in pyrite or arsenopyrite doesn't yield to that method. These sulfide minerals fracture differently from quartz, often shearing or smearing across fracture planes instead of cleanly exposing their contents. Worse, fine gold can end up smeared into the dust, nearly impossible to recover unless you're using mercury, which is both dangerous and legally restricted in many regions. Even if you pulverize the sample to flour consistency, the gold may remain chemically bonded inside the iron-sulfur matrix. It's not a mechanical problem at that point, it's a chemical one. This is where roasting proves its worth. Heating the sulfides to oxidation temperature fundamentally alters the mineral structure. Sulfur is driven off as gas, and the iron oxidizes into friable reddish powders like hematite. The structure collapses, making any encapsulated gold accessible by pan, sluice, or acid test. This transformation simply can't happen through crushing alone. There's also the danger of misidentifying your result. Unroasted pyrite-rich quartz may yield shiny flecks after smashing, but without roasting, these could be chalcopyrite or mica, both of which mislead the eye. Roasting, by altering their color and texture, strips away that ambiguity. True pyrite will oxidize into reddish-brown residue. Mica will not change significantly. This gives an additional diagnostic layer. Not only does roasting free the gold, it reveals whether your sample even had pyritic content worth pursuing. Experienced fieldworkers often perform a crush-roast pan sequence. Crush a small sample, roast it with direct heat, and then pan the remains. This combination helps assess both gold presence and accessibility. If gold shows up post-roast, it's a strong indication that sulfide liberation was necessary, and that larger samples may justify processing. Roasting isn't silent chemistry. It's a spectacle of change if you know what to look, smell, and listen for. When done correctly, a sulfide-bearing quartz sample undergoes dramatic and progressive visual shifts that mark each stage of gold liberation. The first cue comes early: a subtle color transformation from metallic luster to dull oxide tones. Bright brassy pyrite dulls, darkens, and eventually reddens. Silvery arsenopyrite shifts toward gray-white crusts as arsenic is driven off. These are not random burns but structured decompositions, each signaling bond breakdown within the mineral lattice. The second signal is olfactory. A strong, acrid odor fills the air, distinct from wood smoke or heated rock. If you smell sulfur dioxide sharp and choking, pyrite is oxidizing. If there's a garlic-like edge to it, arsenopyrite may be breaking down, a cue to increase distance and ventilation. This sensory input isn't just incidental. It tells you real-time that volatile compounds are exiting the rock and that the reaction zone is active. It also warns when to back off, especially in confined or wind-still environments. As temperature stabilizes in the 600 degrees C range, structural changes become more evident. Quartz around sulfides may begin to crack audibly or spall as internal stresses release. Rust-red halos form around once metallic inclusions, and the material becomes increasingly brittle. What began as dense, resistant fragments begins to flake, crumble, or fall apart under light pressure. This is ideal. You want the sulfide matrix to fail without melting the quartz, which would seal in values again. Sometimes, faint golden specks may appear on freshly fractured surfaces after cooling. These are not always gold, but they warrant testing. A loop inspection can show whether the specks deform under pressure, as gold does, or shatter, as pyrite or mica will. Roasted specks may stand out due to contrast with red oxides, making them easier to spot than in raw ore. Color bands also evolve. In multi-generational quartz veins, earlier cleaner quartz may remain unchanged, while later-stage mineral-rich pulses oxidize dramatically. This contrast can help you map roasting effectiveness across your sample. Uneven oxidation suggests airflow issues or temperature gradient failures, signals to adjust your next roast batch. Post-roast, the sample should feel lighter in hand, a sign that sulfur and volatile metals have been driven off. Break the rock and inspect interior zones. If oxidation is uniform throughout and no unreacted metallics remain, you've achieved a full roast. If parts remain metallic, you'll need more time or better airflow. Roasting quartz to expose gold doesn't require an industrial setup, but it absolutely demands care, control, and respect for the byproducts involved. Hobbyists and small-scale prospectors have long used basic tools to achieve reliable results, provided they manage temperature and airflow with precision. The key is to maintain sustained heat, 500–700 degrees C, in an oxygen-rich environment while containing both the rock and its emissions. Fortunately, this can be achieved with common gear, propane forges, refractory-lined kilns, or even brick-built roasting pits fueled by charcoal or gas. The most straightforward method is a small propane-fired forge or jewelry kiln with a vented hood. These setups allow fine temperature control and ample oxygen access. A stainless or cast-iron mesh tray elevated slightly above the base holds the broken quartz fragments in a single layer. A consistent flame maintains the necessary heat, while the open chamber ensures oxidation proceeds fully. It's critical not to overload the chamber. Stacked rocks insulate each other and cause uneven roasting, leaving sulfides intact in the core. For those working remotely, a homemade roasting pit built from fire bricks or natural stone can suffice. A base layer of lump charcoal provides heat, while a secondary layer of quartz spaced on a grill or mesh absorbs direct flame and airflow. A blower or hand-pumped bellows increases oxygen delivery, mimicking forge conditions. This method is less efficient but viable in field scenarios where transportable kilns aren't practical. Still, attention must be paid to airflow. Oxygen-starved fires will under-roast, producing blackened cores and retaining sulfur. Torch roasting is another field technique for small samples. A handheld propane or MAP gas torch directed at quartz fragments in a steel pan or crucible can reach target temperatures quickly. This is ideal for testing samples before committing to a full batch. However, torch roasting tends to be localized. Only the direct flame zone oxidizes fully. Rotate or stir fragments frequently, and watch for visual cues of complete roasting, reddish crusts, brittle matrix, and sulfur odor dissipating. Containment is essential. Never roast in a sealed container unless it's specifically engineered to vent gases safely. Sulfur dioxide, SO2, and in rare cases, arsenic compounds can be hazardous, even in open air. Always roast in ventilated outdoor spaces, away from buildings, pets, or people. Wearing an N95 or better respirator is recommended, especially if you suspect arsenopyrite is present. Wet down surrounding soil post-roast to fix any particulate residue. Legal considerations vary by region. In the US, small-batch rock roasting for personal use is typically unregulated unless arsenic-bearing materials are involved or the roasting is done in residential zones. Always check state mineral and environmental codes. Some jurisdictions restrict open burning or material processing, even on private land. Without oxygen, roasting is just heating, and heating alone won't liberate gold from sulfides. The entire process of sulfide decomposition depends on oxidative reactions. If air can't reach the reacting minerals, the sulfur doesn't leave, the iron doesn't oxidize, and the crystal structure doesn't collapse. That's why airflow isn't just helpful, it's critical. Whether you're using a forge, kiln, or open pit, the rate and direction of airflow determines how completely your pyrite or arsenopyrite converts to friable oxides, and thus, how much gold becomes accessible. In a properly vented setup, oxygen continuously feeds the chemical reaction, allowing sulfur to oxidize into SO2 gas and escape. The resulting heat sustains further oxidation, producing hematite from the iron. This self-reinforcing cycle continues only if fresh oxygen reaches all surfaces of the ore. In poorly ventilated systems, such as sealed crucibles, enclosed pots, or overly packed forges, air stagnates and partial oxidation occurs. Instead of hematite, you might end up with magnetite Fe3O4 or pyrite Fe-XS, both of which retain sulfur and resist gold release. Telltale signs of poor airflow include uneven coloration. Some quartz fragments will turn red and friable, while others remain metallic or blackened. Another indicator is sulfur odor that lingers without diminishing, meaning gases are building up rather than being carried away. Cracking open under-roasted samples often reveals shiny sulfides preserved inside, shielded from air by outer layers. This is common in batches roasted in closed metal containers or in kilns lacking a draft source. To avoid this, always elevate ore on mesh or perforated trays and allow flame or hot air to flow around and under it. In field-built pits, the shape of the fire chamber influences oxygen flow. A trench design with opposing air inlets works well, especially when paired with a blower or bellows to push fresh air through the coals. Orienting your fire to take advantage of prevailing wind can also help. For torches, oxygen delivery is built into the gas mixture, but the key is coverage. Move the flame continuously to avoid hot spots and allow ambient air to interact with each section. It's not only oxidation that suffers without airflow, cooling does too. Post-roast, allowing the material to cool slowly in ambient air is crucial. Rapid quenching in water or sealing in a metal container prevents microcracks from forming, which are essential for releasing residual gold particles. The thermal contraction from slow cooling opens fine fissures in the quartz and oxide shells, expanding pathways for mechanical and chemical recovery later. Proper airflow also helps avoid dangerous accumulations. In the presence of limited oxygen, some sulfur species convert to thiosulfates or elemental sulfur rather than gas, creating sticky residues that can inhibit further roasting or contaminate leach solutions later. Worse, in very low oxygen environments, carbon monoxide can build up, particularly if burning charcoal indoors. Always roast outside or under a vented hood with carbon monoxide alarms in place. The moment heat is removed from a fully roasted quartz sample, the next critical transformation begins, not in fire but in silence. As the mineral mass cools, it contracts. This thermal contraction, often overlooked, creates internal stress differentials between quartz, oxides, and any metallic inclusions. Since each material has a different coefficient of thermal expansion, the result is a web of microfractures, tiny, often invisible cracks that propagate along the weakest interfaces. These fractures are what finally expose the gold, not the heat alone. Quartz, being relatively stable, contracts slowly and uniformly. But hematite and limonite, the iron oxides formed during roasting, shrink more rapidly. If gold is present, either as tiny liberated grains or residue from decomposed sulfides, it doesn't contract in sync. The result is mechanical strain along boundaries where gold meets oxide or oxide meets quartz. These zones split, tear, or flake depending on the cooling rate. A slow air cool, over 30 to 90 minutes, maximizes this effect, creating widespread cracking that exposes previously sealed gold pockets. The post-roast texture becomes diagnostic. Crushed by hand or tapped lightly with a hammer, the rock should break along natural weaknesses, seams of hematite, spiderweb fissures, or discolored fault lines. What was once a tight matrix now crumbles more easily. In some cases, flecks of gold may detach during this stage, their once protective shell now converted to brittle oxide. These fragments may be invisible until concentration methods like panning, sluicing, or acid etching are applied. It's also at this stage that another test becomes meaningful: acid reaction. Drop a small amount of white vinegar or diluted hydrochloric acid onto a cooled fragment. Iron oxides fizz lightly or stain the solution. Quartz remains inert. Gold, of course, does not react. Areas that fizz or bleed orange into the liquid point to previous sulfide zones, precisely where gold may now be exposed. These tests allow a focused follow-up, re-roasting stubborn segments or targeting gold-rich zones for further processing. Importantly, avoid rapid cooling. Dunking hot rock into water or using forced air coolers may seem efficient but risks shattering the sample before full fracture pathways develop. Worse, it can drive steam into cracks, potentially obscuring visible clues or creating false surface alterations that confuse further testing. Patience in this phase yields clarity. Lay samples out on heat-resistant surfaces and allow them to return to ambient temperature naturally, observing both texture and smell. Sulfurous odor should fully dissipate by the end of this stage, another sign that volatile compounds have escaped and roasting is complete. Even after a successful roast, color changes complete, odor gone, texture crumbled, you may find the pan yields little or no visible gold. This isn't necessarily failure. It may simply mean the gold is still present, but in a form that doesn't separate easily by gravity. If gold was too fine, submicroscopic, or still trapped in oxidized residues, roasting alone won't extract it. This is where leaching, the chemical dissolution of gold, enters the equation. Done carefully, it can recover what roasting only revealed. But leaching comes with a risk-reward balance. The upside is recovery of gold too fine to see or pan. The downside is chemical exposure, legal oversight, and potentially false results if not executed with precision. The goal isn't to dissolve everything, but to selectively dissolve gold while leaving oxides and silicates behind. For hobby-scale operations, the most accessible leach option is a peroxide vinegar solution. This mix, commonly 3% hydrogen peroxide and white vinegar in a 1:1 ratio, generates peracetic acid, a mild oxidizer that can dissolve trace gold over time. It works best on finely roasted material where gold has been fractured out of host minerals. The reaction is slow, often several days, and requires stirring temperature control around 40–50 degrees C for efficiency, and post-process filtering through coffee filters or fine mesh. A stronger but still legally accessible method uses a commercial thiosulfate leach. Sodium thiosulfate, combined with a copper sulfate catalyst and ammonium hydroxide for pH control, dissolves gold without the toxicity of cyanide. This method is preferred by small-scale miners and research labs for refractory ores. It requires close pH monitoring, ideal range, 9–10, and typically runs over 24–48 hours. Gold is then recovered by precipitation, commonly using zinc powder, which drops gold out of solution as a fine metallic sludge. The risks arise when leaching is attempted without roasting. Sulfides left unroasted consume oxidizers rapidly, often binding gold even tighter. Worse, unoxidized arsenopyrite can release toxic arsenic compounds into leach solution, creating hazardous waste. This reinforces why roasting must precede leaching in any sulfide-rich ore. The more complete the roast, the safer and more effective the leach. Field missteps often involve acid overuse. Muriatic hydrochloric acid, for example, does not dissolve gold on its own, but it will dissolve iron oxides and confuse color tests. Some hobbyists see a yellow solution and assume gold is present when it's actually iron or organic staining. Only with confirmatory steps, precipitation, weighing, or spectroscopy, can you confirm leach success. Legally, leaching at home with commercial or homemade reagents exists in a gray zone. Most regions allow small-batch chemical use for personal prospecting, but disposal regulations are strict. Neutralize waste with baking soda, sodium bicarbonate, filter solids, and never pour into drains or soil. Document your methods and keep waste sealed until you can deliver it to a hazardous materials drop-off site. When leaching reveals visible sediment, gray, tan, or yellowish, dry it, weigh it, and compare it to your starting material. Often, even a few milligrams per kilogram roasted can justify further recovery, or at least confirm the presence of gold in what appeared to be barren rock. Once your roasted quartz has cooled and crumbled, a simple magnet becomes a surprisingly powerful diagnostic tool. It won't attract gold, but it will quickly clear the field of remaining iron-bearing minerals like magnetite, hematite in trace amounts, or residual pyrite. This step not only helps refine your concentrate before panning or leaching, but it also acts as a reality check on how complete your roasting process was. If magnetism remains strong, you may not have oxidized your sulfides fully. If it's absent or faint, your gold may now be free to recover. The method is straightforward. Use a rare earth magnet, neodymium preferred, wrapped in plastic or placed in a bag to prevent contamination. Sweep it slowly over the crushed and sieved roasted material. Anything attracted to the magnet is not gold, it's likely unoxidized iron minerals. Pyrite, for example, often survives incomplete roasting and clings tightly to a magnet. Magnetite, which may have formed from under-roasted pyrite, behaves similarly. Hematite is weakly magnetic but may still show response in high-purity forms. In a properly roasted sample, magnetism should be minimal. The red to brown powdery material you see, often hematite or limonite, is either weakly magnetic or not magnetic at all. If your magnet sweep returns large amounts of black sand or hard particles, it signals incomplete oxidation. In this case, consider re-roasting those fractions at slightly higher heat or for a longer duration, with more airflow. This step increases your overall recovery rate by converting partially processed sulfides into their friable oxide forms. The magnet sweep also doubles as a sorting mechanism. In mixed samples, especially those from placer sources where black sands may mix with roasted fragments, a magnet helps isolate inert heavies from potential values. Gold, being dense but non-magnetic, will remain behind in the non-attracted fraction. This allows your next step, panning or leaching, to focus solely on materials that might contain liberated gold. Another use of the magnet comes before roasting. A pre-roast magnet test can help assess sulfide content. If a sample is magnetic in raw form, it likely contains pyrite or magnetite, potentially non-gold bearing. After roasting, those same particles should show a reduced or altered response. If magnetism persists in the same pieces, you're dealing with stubborn oxides or incomplete decomposition. This before and after contrast gives insight into mineral conversion and roasting effectiveness. It's also worth noting that some artisanal miners use magnetic separation as a partial pre-concentration step, especially in gold-bearing sulfide ores with high iron content. The idea is to remove bulk iron minerals before chemical processing, reducing reagent consumption and waste volume. Still, the magnet won't tell you everything. Non-magnetic materials can still be worthless, and magnetic losses don't always mean gold presence. It's a filter, not a final answer. But by removing magnetic noise, you sharpen your focus on what remains: oxidized residue, potential gold specks, and mineralized zones ready for gravity or chemical recovery. In the field, success begins with smart selection. Roasting is time and fuel intensive, so choosing the right quartz samples before transport is critical. Fortunately, certain surface clues offer surprisingly reliable guidance. The trick is training your eye to separate random iron staining from structurally significant indicators, features that suggest sulfide inclusion and, potentially, gold entrapment. When visible gold isn't present, it's these subtler diagnostics that separate barren rock from high-probability ore. Start with quartz texture. The most promising pieces are rarely pure white or glass clear. Instead, look for quartz with a mottled, granular appearance, especially where fine-grained specks of gray, brassy, or black minerals dot the surface. These inclusions often represent sulfides like pyrite, chalcopyrite, or arsenopyrite. Use a loupe to check for cubic or octahedral patterns, pyrite's classic hallmark, or streaky gray veins suggestive of arsenopyrite. If these inclusions appear within angular fracture networks, you're likely looking at multi-phase mineralization, where gold could be embedded. Fracture character is another major clue. Roasting candidates often show iron oxide halos or spiderweb rusting along fine fracture lines. These patterns are not cosmetic weathering, they're pathways where sulfides oxidized, hinting at deeper entrapments. Sharp fractures with red or yellow crusts suggest internal chemical activity, not just surface staining. In contrast, quartz that's broadly orange or brown with no structural context is often just weather-stained and barren. Density also offers a rapid field test. Pick up 2 quartz samples of similar size. If one feels noticeably heavier, it may contain sulfide minerals or metallic inclusions. Gold adds significant weight even in small quantities, and iron sulfides increase rock density substantially. While not definitive, this weight-in-hand test is one of the most underutilized tools by novice prospectors. Field magnetics can further refine your sort. A neodymium magnet passed slowly over the sample will react to pyrite, magnetite, or partially oxidized pyrite. A mild pull is promising if paired with the other indicators above. Strong attraction without structural rusting may point to non-gold-bearing magnetite, still useful information, as it helps you triage what not to carry. In known gold zones, location reinforces your sample choice. Quartz near fault contacts, shear zones, or historical diggings holds more promise than float rock pulled randomly from a wash. Pay special attention to quartz veins that cut across darker host rock, like greenstone, slate, or diorite, as these often mark old hydrothermal channels where metal-laden fluids once traveled. Field acids can also help. A drop of dilute hydrochloric acid will fizz on carbonate gangue but not on quartz. However, it can also highlight iron reactions. Light bubbling or staining on a sulfide-veined rock confirms oxidation is ongoing, and you may be looking at the oxidized cap of a richer system. Lastly, take field notes. GPS mark, sketch, or photograph promising outcrops and carry back a mix of fully intact and fractured samples. The goal is to get both context and variation, coarse and fine-grained zones, heavily oxidized versus lightly veined. This allows comparative roasting later, where sample behavior can be matched against field observations. There's a subtle moment after roasting when you pick up a once heavy rock and feel less. The sample, formerly dense with sulfides, now feels almost hollow. This contrast isn't your imagination. It's a powerful, repeatable clue that roasting has altered the rock's internal structure. More than a curiosity, this weight shift is a practical test that tells you whether sulfur and iron have been driven off, and whether gold, if it was present, might now be retrievable. The weight-in-hand post-roast test is low-tech but surprisingly reliable in narrowing down which samples deserve further processing. Before roasting, quartz rich in pyrite or arsenopyrite feels unnaturally heavy for its size. That's because pyrite-specific gravity (5) and arsenopyrite (6) add significant bulk compared to quartz itself (2) 65. If your sample has visible sulfides or passes the magnet test, it likely carries this extra heft. After roasting, these dense sulfides are converted into iron oxides, such as hematite (5) or limonite, but crucially much of their mass escapes as gas, sulfur dioxide or arsenic trioxide. What remains is structurally weaker and significantly lighter. That loss is tactile. Roasted quartz with fully oxidized sulfide zones will often feel brittle and light, even airy compared to its pre-roast self. This is especially noticeable in samples with heavy staining or visible oxidation halos. It's also diagnostic. A quartz sample that still feels dense after roasting may contain unconverted sulfides, especially in its core. This flags it for re-roasting or extended time at temperature. But the real value comes when comparing samples. Suppose you roasted 3 pieces from a single vein system. One feels sharply lighter and crumbles easily, another feels unchanged in weight and resists fracture. That comparison gives you an immediate triage. The lighter sample likely completed oxidation and may now release gold. The heavier one may still need time or better airflow. This helps you avoid wasting acid or panning time on samples that aren't ready. If you're using a scale, even better. Weighing before and after roasting quantifies mass loss, often 5–15% in sulfide-rich quartz. A sample that loses 10% by mass is a strong candidate for follow-up testing, especially if discoloration and texture changes match expectations. Consistent losses across batches suggest uniform roasting. Variability signals either compositional differences or inconsistent heat penetration. The weight test also plays into downstream decisions. When building up concentrates, you want material that's already shed excess sulfur and iron. Roasted samples that feel lighter and more friable pan better, leach cleaner, and yield more reliable assay results. They're less chemically reactive, which improves leaching efficiency and reduces the risk of fouled acid or peroxide mixes. Still, one caution: don't confuse lightweight with value. Volcanic rocks like rhyolite or weathered gossan can also feel light but yield nothing. That's why the weight test works best as a contrast, comparing the same sample pre- and post-roast. It's the difference that matters, not the absolute mass. It's one of the more deflating outcomes in small-scale prospecting. You select a beautifully rust-streaked piece of quartz, roast it with care, watch it crumble into oxidized fragments, and then nothing. No specks in the pan, no density shifts, no promising residue under the loop. The rock roasted perfectly, but the gold never appears. This isn't failure, it's a learning moment. Because not all rusty quartz is gold-bearing, and not all sulfides host valuable metal. Understanding the false positives is essential to refining your field selection and avoiding wasted effort. The most common culprit is iron-stained quartz formed without sulfide inclusions. Quartz exposed to surface weathering can take on vivid orange, yellow, or red colors simply through contact with iron-rich groundwater or nearby oxidized rocks. These stains are superficial, often coating the quartz in thin films or penetrating only the first few millimeters. Cracking open these rocks reveals clean, white interiors, uninterrupted by mineralization or metallic grains. Roasting these does little more than dehydrate the outer crust, and in some cases, exaggerates the misleading oxidation patterns. Another false signal comes from quartz with iron-rich accessory minerals like biotite or hornblende, which can weather into rust tones but have no connection to hydrothermal sulfide deposition. These minerals aren't associated with gold formation, yet they contribute to the visual complexity that tempts many into collecting useless samples. In crushing or roasting, they show no change beyond color enhancement, and they leave behind inert powder and no density shift. Even real pyrite can lead you astray. Not all pyrite is gold-bearing. In fact, most pyrite forms in non-auriferous environments, especially in sedimentary or volcanic layers where sulfur and iron bond independently of precious metals. These pyrites roast well, producing textbook red iron oxides, but their interiors were always hollow of value. Without context, even perfect cubic pyrite crystals in quartz can mislead. This is where geological setting matters more than surface clues. To avoid these traps, a few practical tests can save effort. First, always break a sample open before committing to roasting. If rust is only surface deep, or if the interior is clean quartz with no embedded grains, it's likely barren. Second, perform a pre-roast magnet test. If no magnetic response occurs, the sample may lack iron sulfides entirely. Third, sieve a small amount of crushed material and pan it gently, even unroasted, or may shed minor values if gold is loosely attached. Another useful tool is the shortwave UV lamp. Some barren quartz fluoresces, but gold-bearing quartz usually doesn't. Instead, subtle phosphorescence around fracture zones can sometimes highlight zones of alteration tied to mineral deposition. It's not definitive, but when paired with rust patterning and density clues, it adds another layer of pre-roast triage. Roasting takes time, energy, and care, so narrowing your focus to high-probability material saves more than just resources. It sharpens your geological intuition. Every false positive fine-tunes your eye, making the next selection smarter. Because when gold is present, the tests begin to converge. Color, weight, structure, magnetics, and crush behavior all point in the same direction. While roasting quartz is often seen as a benign part of small-scale prospecting, it can quickly cross into legally sensitive territory, especially when the target minerals include arsenopyrite or other toxic-bearing sulfides. Most hobbyists focus on gold and iron oxides, but forget that some of the richest gold ores also contain trace arsenic, lead, antimony, or mercury. These elements, when heated, don't just oxidize, they volatilize, producing airborne compounds that are regulated under environmental law in most jurisdictions. The clearest line is arsenic. Arsenopyrite Fe(S), a common host for refractory gold, breaks down into arsenic trioxide as 2O3 when roasted. This compound becomes airborne at relatively low temperatures, till 400 degrees C, forming a white, pungent vapor that can travel on wind or settle into local soil. Even in small quantities, arsenic emissions are a known carcinogen and subject to regulation under air quality, hazardous waste, and public safety statutes. In many U.S. states, open-air roasting of arsenic-bearing ore is explicitly banned, and even contained operations may require permits. But the risks don't stop at arsenic. Roasting galena PBS, for example, releases lead oxide fumes. Cinnabar HGS, once used in mercury mining, releases elemental mercury vapor at only 357 degrees C. Even roasting stibnite Sb2S3 can produce antimony trioxide, another regulated compound. These reactions don't require large-scale operations to create problems. A single poorly chosen rock with mixed sulfides, roasted near residences or waterways, can trigger long-term contamination. Identifying these minerals visually is possible but not always reliable. Arsenopyrite tends to have a steely gray appearance with a slight iridescent tarnish and a distinctive garlic odor when crushed. Galena is lead gray and very dense, with perfect cubic cleavage. Stibnite appears as metallic gray needles. If any of these minerals are suspected, or if your roasted sample smells unusually sweet, acrid, or metallic, it's time to reconsider the batch. Legal exposure depends on jurisdiction. In the U.S., the Clean Air Act and Resource Conservation and Recovery Act, RCRA, govern emissions and waste handling. Roasting that emits hazardous gases may fall under open burning prohibitions, even on private land. In Australia, Canada, and parts of Europe, similar statutes exist, and local mining regulations may enforce even stricter controls in known mineralized regions. Always check with your state or provincial Department of Natural Resources or Environmental Protection Office before conducting any thermal processing. To stay within legal and ethical bounds, several safeguards are essential. Roast in rural, ventilated zones away from homes or water sources. Avoid any material suspected of containing arsenopyrite or other volatile heavy sulfides, unless in a controlled facility with fume extraction. Use small batches and test mineral identity beforehand using acid, loop, or spectrometer tools. Collect and seal ash or residue for proper disposal, not roadside dumping or garden use. Document your process if you intend to scale up or sell processed ore. This helps establish good faith if regulators inquire. In many cases, the solution is selective sampling. Focus on pyrite-bearing quartz without arsenic associations. These rocks roast cleanly and produce minimal emissions. Alternatively, consider mechanical or wet chemical methods that don't involve heat, such as thiosulfate leaching or gravity concentration, especially in urban or regulated areas. The goal isn't to scare you out of roasting. It's to ensure the value you uncover doesn't come at legal or environmental cost. Because when your sample finally delivers visible gold, the last thing you want is a regulatory headache overshadowing your find. And when that moment comes, you may want more than just your pan, you'll want lab data. So how do you know when to send roasted concentrates for assay? And what can those tests really tell you?